right, so my name is Logan. I'm from a company called Chronologic. We've been working on a project called the Ethereum Alarm Clock. It's been around for a while. It's been around before we took it on. And I'll be presenting about what this project does and what the problem it tries to solve is. The best summary of the alarm clock is that it's trying to solve this very base layer problem in a decentralized on-chain way on Ethereum. So the problem it's trying to solve is the ability to schedule transactions and have those execute for you without actually having to be present at the computer and without actually having to press the button. So the way we've done this is through this open source smart contract protocol. It was originally created by a developer named Piper Merriam. We kind of adopted it from him. It's been in states of working and not working for a little while, and we have it up and working again, so we have it deployed on the Coven testnet. And we're right now waiting for a security audit to go ahead and deploy on the mainnet. And just to kind of judge the audience, how many are developers? Okay, cool. And are you guys, are you Ethereum developers? Familiar with smart contracts? Yeah? Okay, cool. So if you're a developer, you might want to use the Ethereum alarm clock, and I'll show you how in a little while. So here's a picture of Piper Merriam giving the original presentation on the alarm clock at DevCon 1, which was one of the original Ethereum conferences. So why the Ethereum alarm clock? So we simply want to be able to put in a set of parameters about when we want a transaction to be executed and what kind of transaction we want that to be. So whether we want to hit a smart contract to trigger something or simply send some value to someone for a rent payment or for phone bill. We want to do this, and we want to do it in an on-chain, trustless way. So the use cases for this are nearly infinite. Anything from buying tokens from an ICO contract without having to stay up really late at night because of time zones or things like that, to routine payments, phone bills, rent payments, putting this into your dApp, integrating this on like a lower level. So if you have a user send one transaction, maybe that transaction also schedules another at the same time. We want wallets to integrate this, and we want people to run what we're calling time nodes, which are the way we can actually guarantee that these transactions will be executed when they're set to be executed. And I'll go into those in a little bit, but first I want to just announce this really cool thing we're working on. I don't know if people know MyCrypto. It's a fork for my Ether wallet. Yeah, and we're right now preparing a pull request to get the Ethereum alarm clock natively integrated into their main transaction page. And we've been like working with them, and we're super excited to finish up this pull request and send it to them and get it actually in the MyCrypto wallet. And I'll give you guys a demo of that a little bit later as well. But first I'll go into kind of like a deep dive of like how it works technically. So on the problem that the Ethereum alarm clock solves on like a foundational level is that smart contracts can't execute themselves. Only users who hold a private key to that account are the ones who can execute transactions. And what we want to happen is for smart contracts to be able to just be executed when we want them to without actually having to press that button and execute them ourselves. So this is something that's foundationally you can't do in Ethereum. Like there's just no way to do this. You can do it on a server, you can write like a cron job, but the problem with that is that your server might fail, it could go down. Okay, then you can have 2 servers. What if both of those fail? What if we just have a decentralized server, and it's Ethereum, so why not? And that's kind of where we're getting the inspiration here. So how does this work? So the flow of this is so a user will schedule a transaction with all of the parameters that they want. They'll send this to a smart contract on the Ethereum blockchain. This contract will deploy another contract holding all this data. And then we have a market of time nodes, which are these off-chain clients. So they are running on a server, but we want people to run these, like it's completely open to run them. And we incentivize these time nodes to be ran. So hopefully people want the incentive, so they run these time nodes all around. And these time nodes then are watching these new contract deployments. And every time a new contract is deployed, they'll note it, take down the address, and take down when that contract should be executed. And when that contract is up to be executed, the time node will send the execution transaction, and it'll execute that transaction exactly how the user scheduled it to be executed, because everything is stored on chain. So because Ethereum is immutable, you can't change it once a contract is deployed. The person who scheduled that transaction has a guarantee that that transaction will be executed exactly how they set it to be executed. So the smart contract architecture can be kind of broken up into 4 major pieces. The scheduled transaction, so the parameters that the user sets are the transaction request on the far side. We have it's called transaction request core there, because what actually happens is each transaction delegate calls to this central contract and just kind of takes all the logic from there. So that's why that one's called core. And then we have, on the other end, the schedulers, which are the contracts that users will be talking to. And these are the ones that deploy the transaction requests. And then we have the lower level request factory, which does a lot of the heavy lifting work, and a request tracker, which is basically an on-chain database that stores all of these contracts, all of the contract addresses. And this is just another way to look at it. So users will be talking to the scheduler, and there's a lot of logic underneath that's being triggered. And here is the contract dependency chart. So there's a lot of libraries written in Solidity that are being talked to for all of this logic. It's one of the larger Solidity code bases. I guess we can't really say it's in production right now because it's just on the testnet, but we've been using it on the testnet for about a month now, and like I said, we're just waiting for a security audit, so hopefully soon it'll be in production. And so I'll go into a little bit of how the code works. So starting with the scheduler, here's the interface for that. Like I said, this is what users will be talking to feed in the parameters. It takes in the to address, which is the recipient for this transaction to go to, some bytes, which will be the call data. So this is where you can put in encoded call data to trigger a smart contract function, for example. And then some uints, and these are stuff like the gas price, the value that's being sent, and a couple other things specific to the protocol, which I'll go into in a second. Just went over that. Okay, here, this middle timeline. So each transaction, when it's deployed from a scheduler, has a lifeline until it reaches the execution window, which is when it's actually going to get triggered by a time node. Before that, we have a claim period, which is something that we're kind of like maybe tweaking here from the way it works now. I'll go into that a little bit later. But then we have that's like the timeline for a transaction. These are the integer arguments broken down. So the gas, the value, the window size, so the size of the execution window, how many blocks will there be for this transaction to be executed, and the window start is what block number or what timestamp will this window begin. The gas price, the fee and the bounty. So the fee is a way for front-end integrations to kind of set this and then get a payout for integrating this into their application. So it's similar to maybe like the Shapeshift like affiliate thing where My Ether wallet can put a Shapeshift button in and they get like 0.5% from every time someone uses it. So if people want to put this and integrate this into their wallets or app, they can put a small fee there and send it to their own address. It's something that is lifted higher than the protocol, and it can be set by the person integrating it, so from the JavaScript essentially. And then the bounty, so this is the value that is actually incentivizing the time nodes to execute transactions. This is how we can give guarantees to users that transactions will be executed, because they're putting some stake there to say, if you execute my transaction, I will give you money. And this is how we can incentivize more people to run time nodes to be executing these transactions because they want the bounty. And then the required deposit is from the claiming system. It's just a value that you put in to if someone wants to claim a transaction, they kind of just stake some money there and they can claim it. Claiming comes as a first come, first serve kind of thing. So there's some logic worked in where, depending on when during the claiming window a transaction gets claimed, there's a payment modifier. So only at a certain time really is a transaction profitable to be claimed. So theoretically, every time node will attempt to claim this transaction at this exact time. So it really just comes down to like whichever transaction gets included into the block first. And this is how we've kind of solved the claiming mechanism for now. We're looking at tweaking this in certain ways because preferably we'd have something where it's not just whichever transaction is first in a block. Preferably we'd have a way to divvy out claims to different time nodes. About the request factory, so this is just the lower level to the scheduler. It's just what actually is deploying contracts. The really cool thing about the request factory is that the contracts that it produces are just these small pieces of bytecode that just essentially take every call into it and delegate calls that into another contract, and that's called the clone factory pattern. It's a really great way to save on gas costs if you're deploying a lot of similar smart contracts. So when we integrated that, we were spending 2.5 million gas to deploy each new transaction request, which is a huge amount. We do a lot of storage calls, so that's why. But just implementing this one change alone brought it down to under 1 million. So that's a huge, significant optimization for us. So if you need to optimize, I highly suggest you look into the clone factory. This is the interface. I can just walk through that. So like I said, the transaction requests are what's holding the parameters for each scheduled transaction. So one cool thing about this is if the smart contract is what's calling the final transaction, that means that the smart contract will be the message sender in this situation. So there's a problem, for example, if this contract is buying tokens from an ICO contract, that means that this scheduled transaction contract would become the owner of those tokens and just basically get stuck there because it's just a dummy contract. So how can we get these tokens out? And so we came up with this really cool proxy function, which essentially just routes a transaction that's fed to another contract and can do things like just transfer those tokens out. So it's a pretty simple function. It just takes in where it's going to go and the data, so what function on a smart contract that's going to call, and it just calls that out of that contract. All right, so that's from the scheduling aspect, from the user who's going to be scheduling transactions. But there's also another side of the Ethereum Alarm Clock for the executors or the time nodes. So I'll talk a little bit about that end of it. There you go. So the goal is to create a decentralized market of people running these time nodes. So how can we accomplish that? I've already talked about the bounty. Another way we've tried to help out here is we've made the client open source. We've also built this into the dApp that we've been working on. So originally you could only run one of these from the command line, which meant that developers could do it really easily. But no one else could. So because we want to make sure that we're creating a open, decentralized market and there's not any point of failure. We also built a browser time node. So people can just open up a browser window and click start and fund the account a little bit, and they'll be executing transactions. So this creates like this competitive market of people running these nodes. We've tried to make this crypto economically sound. So the person who schedules a call doesn't care who really executes that. They just kind of put some money up there and say, whoever gets to it, execute it. And on the time node side, no matter what this scheduled transaction does, or even whether it succeeds or fails, they'll always get paid at least the gas plus the bounty. So the bounty can be set by the user to be really low or really high. But no matter where it's set, really, as long as it's above 0, the executing time node will make profit because they're always at least getting back the gas too. So we've also been working on JavaScript tools. So people developers who would like to integrate this into their dApp, they can use our open source JavaScript tools. We've kind of divided them into 4 different packages. We have a low-level library. So if you want to interact with the contracts, we have a client, which contains the time node logic. And then we have the CLI, which is the command line interface for running a time node or scheduling a transaction. These are available on NPM. If you want to see the source, they're on the Ethereum Alarm Clock GitHub repository. Here's a quick example of how you'd use this. So anyone who's developed on Ethereum probably knows Web3. It's just the way to bring Ethereum usage into JavaScript land. So you instantiate Web3 like normal. You pass this into the EAC library for Ethereum Alarm Clock. The EAC library will right away recognize which network that this Web3 object is on and pull up the latest contracts from the repository. And then right away you can use it to get those contracts. And here we have, we are getting the request factory and we're pulling a list of the requests from a certain block. And we're just pulling the first one and we're saying execute it. So really we should be checking if that transaction can even be executed, but here we're just executing it. But it saves up a lot of boilerplate and it makes it really easy to start using this. So right now I'll give a demo on the time node that we've been building. There we go. Okay, so this is available on app.chronologic.network. So we've essentially just made a dashboard to make it really easy to schedule calls, to look up those calls based on when they'll be executed in a scanner, and then to run a time node. So I'll just quickly walk through scheduling a call here. So it integrates with MetaMask, and we're on the Coven network. So
can you make it a bit larger?
Yeah. Is that good? Okay, cool. So so how many people are familiar with MetaMask? Okay. Okay, cool. So so yeah, MetaMask is just a light wallet for interfacing with Ethereum. So we're on the Coven network here. You set the parameters. This looks good. This will happen in about an hour. You set the recipient. Here I'll just use my own address. the amount in Ether that we want to send, gas price in Guai, the time bounty, so how much we'll be paying the executor, it confirms with us that all of these variables are what we want it to be. It tells us how much this transaction will cost to schedule and later be executed. And we schedule it. MetaMask confirms with us. We hit submit. And we wait for this to be mined. So it'll take a few seconds to be mined. Coven is pretty quick. But what it's doing here is deploying that contract. So it does some stuff in the background, and the smart contracts will be deploying this new contract. We can see here it transferred from a few different addresses. So this last one here is the new contract that's been deployed. It's what's actually holding the funds. So this is what we can use to look up info about it. And we've also made a dashboard to look up info about any scheduled transactions. So as long as you know the address, you can type it into here. And it's kind of similar to an Etherscan interface or a block explorer. You can also browse transactions. This sometimes takes a little while to load. But I'll go to the time node. So this is the execution client. Because it's written in JavaScript, we can just run it in a browser. So we did that. And you just click start. And now this is a client that's running as long as you have this window open. And it'll execute transactions from our address. And to make sure that it's running, we can look into the logs. And we see that it picked up a transaction here a few seconds ago. And we can compare this address to the one that we just scheduled. And we see that it's the same. It's 5 BE5FD. So we can see that this client picked up the same transaction that we just scheduled, and in about an hour it'll send the execution transaction and claim the bounty. So that's what we've built to kind of encourage people to start using the Ethereum Alarm Clock. And we're also working on a MyCrypto integration, which is a similar kind of control flow, but will be straight from the MyCrypto main transaction page. And I can show a quick video of that as well. So this is not live yet. This is from our development servers, but this is what we're working on, and we're talking to them, and they're really enthusiastic about merging this in. So hopefully really soon we get this merged into their repository. But this is what it will be like to use the Ethereum Alarm Clock to schedule a transaction. So similar to the normal MyCrypto interface, the block is a field that we added, so the execution block, the time zone, bounty, transaction, sliders. we get the nice green bar from MyCrypto. Just making sure that it's recording. And then if we want to check out the details of that, we can go back to the app at Chronologic.network and get the nice Etherscan looking, Blockchain Explorer looking interface. So there you go. So that's what we're hoping the flow will look like for users to use the Ethereum Alarm Clock to schedule. And so that's what we've worked on up until now. The one catch in that whole thing is that each transaction still costs us just under 1 million gas to schedule. And we think this is still way too high for users to use this. We think it's too much overhead. So we're looking at ways to further optimize it and make it as cheap as possible so people actually use it. And so we're looking into scaling solutions. So we did some research into state channels. It was a hot topic at ETHCC. We were just there. So we were talking to a lot of people. Right now we're still looking into it, but we're more focused on, we kind of decided maybe state channels might not be the best solution for the alarm clock. So we kind of transitioned to what we're calling a stateless client. And so it costs us 1 million gas because we're storing all of the parameters into this smart contract. So what we're looking at doing now, and we're pretty sure this will work fine, is we're going to store everything in IPFS and just store the same hash in the contract. So the way IPFS works, the same hash that's derived from the content is also the location of that content. So we're able to just store that hash and allow time nodes to find the execution parameters just by storing that hash. So we're moving toward that, and we're also looking into more conditions than just time-based execution. So if this, then that kind of execution. If the price of Ether is 6,000 or 600, then execute this transaction kind of thing, which we think might be more possible using this IPFS kind of scheme. And there's a kind of just a diagram of how we're thinking about building this new protocol. So the major change here is that we're just storing everything in IPFS, and instead we're passing the encoded byte data to the schedulers, and instead of storing anything, we're just emitting an event log. And then we expect the time nodes to be watching these new events. And that's as far as we're at right now. If anyone would like to ask a question.
Is there a reason you're building this on top of Ethereum alone, besides, I don't know, exercise or something like that? I mean, I saw a couple of new blockchains, new solutions that have, I don't know, these stateless things and scalability issues solved through, I don't know, side chains or oracles or something like this. Is there a direct connection why you shouldn't explore these kind of things? Or
so we started building on Ethereum because Ethereum was the most robust smart contract platform, and it was the first blockchain that really something like this could be built on. But now there's a lot of other blockchains that are doing smart contracts, and something like this potentially could work just as well on those platforms as well. So we are kind of looking into that, yeah.
Maybe just a suggestion, take a look at Eternity.
Eternity?
Yeah, it might be, I don't know, for 2 or 3 of your issues, might be a cool solution.
Interesting.
If I understand this correctly, this is the scheduling for one-time call contract only. Have you ever considered about periodic calling of contract? This is usually needed in.
Yeah. So yeah, we are looking for better ways to do it. Right now, what someone would have to do is schedule those calls next to each other. So say this one's going to be executed in a month, this one's going to be executed 2 months from now, kind of thing. But ideally, yeah, we would want to be able to just do one and say every month execute that. We're still looking at a way to do that, so it's a kind of open question. Yeah.
If I got this correctly, this only works now for Ethereum transactions, but later you plan to use, I don't know, contract calls or whatever, and use ETFs for that, for the storage of the parameters.
Yeah, so it does Ethereum calls, but it does arbitrary call data, so it can transfer value or it can call other smart contracts. Was your question about IPFS or?
I mean both. For example, if I'm calling a contract, everything is now saved on your smart contract, the data that I'm sending, right?
Yeah, so it's not really our smart contract. It's a smart contract on Ethereum, and actually whoever schedules it is the owner, and they're the only ones that can cancel that. We don't really, right now we have a kind of kill switch in place, but we're going to take that out. So what's going to happen is we're going to have no way to actually change that or to cancel it. Did that answer your question?
Yeah, I mean, I was worried about the security of the data that would send because only you can change it.
Yeah, only the person who scheduled it can change it, and they do that by canceling that transaction and deploying a new one. But as far as transparency, like that data is on the blockchain, and anyone can look it up too.
Yeah, but the time node calls the contract, your contract directly, or it just executes? I mean, who does the final transaction?
The time node. So the time node looks at what's in the smart contract and executes it exactly as a smart contract. And then there's logic in the Ethereum Alarm Clock logic that checks each of those parameters and that they're being executed as set.
But time node is JavaScript client on browser. Yeah. So anyone can change the code and call contract differently if they wish to be malicious.
Yeah, but the smart contract checks the logic when it's being executed. So if a malicious time node attempts to like send a really high gas price or something like that, that transaction will just fail and get reverted because there's logic in the smart contracts to say if the gas price isn't equal to. Yeah.
So what would be the total cost if you include bounty and gas?
Well, it's always up to like what the user sets, because the bounty can be variable. So right now the gas overhead is just under 1 million gas. So depending on gas price, I think it's like if you send like 1 guai, maybe like 20 cents, like. But it just goes up from there, and it goes up exponentially. And with the IPFS solution, we're hoping to get that down to about 100,000, so 1/10 of that.
And so a lot of the applications are in sort of trading wallets and platforms?
Yeah, both. So exchanges and wallets. We've talked to some exchanges that want to use the alarm clock to do like complex like trading calls and stuff. So yeah.
So if I got this correctly, the hardware requirements for running a time node are practically non-existent.
Yeah, you can actually run it off your phone.
Off a Raspberry Pi or something like that. So put a simple server and contribute to the network and pick up on it.
Yep. We've tried really hard to make that possible. Yeah.
What prevents a time node from being early?
For being early? The same logic in the smart contract. So that checks the execution start window. So if a time node attempts to execute a scheduled transaction beforehand, the contract will say, wait, the block number is below the block number it's supposed to be executed at, and just throw that transaction. Yeah, so that works pretty well. It's just the smart contracts there. Okay, cool. Thank you.